Ever pondered how mathematical analysis influences your everyday life? It's an intriguing question, isn't it? Mathematical analysis, in essence, is the branch of mathematics that deals with limits, infinite series, and the concept of continuity. It's the backbone of many mathematical theories and is deeply intertwined with our daily lives. From simple tasks like calculating your monthly expenses or determining the quickest route to your favorite coffee shop, to more complex activities like predicting weather patterns or modeling the spread of diseases, mathematical analysis plays a crucial role. It's not just about numbers and equations, it's about understanding patterns, making predictions, and making sense of the world around us. Whether it's the derivatives in calculus, the infinite sums in series, or the complexities of topology, each aspect of mathematical analysis serves a unique purpose, contributing to our understanding of the universe. So let's dive into the fascinating world of mathematical analysis and discover its wonders. Imagine you're driving. How quickly you're changing your position is what differential calculus is all about. Picture this. You're on a road trip, cruising down the highway. The speedometer fluctuates as you navigate through varying terrains. Sometimes you're accelerating, sometimes decelerating. This rate of change in your speed or position is a prime example of differential calculus in action. In mathematics, differential calculus is the branch that studies rates of change and the slopes of curves. It's about understanding how one quantity changes in relation to another. This is done using derivatives, which are essentially mathematical tools that measure this rate of change. Think of it as the speedometer of your car, gauging how quickly your speed is changing at any given moment. So whether it's the speed of your car, the growth of a population, or the trajectory of a planet, differential calculus is the mathematical lens through which we view and understand change and motion. In essence, differential calculus helps us understand change and motion. Integral calculus, on the other hand, is like adding up pieces to make a whole. Imagine a pile of sand. Each grain, minute and insignificant on its own, collectively forms a substantial heap. That's the essence of integral calculus, accumulation. It's a mathematical tool that helps us calculate areas, volumes, and more by summing up infinitesimally small parts. If you've ever wondered how engineers calculate the precise amount of material needed for a curved structure, or how physicists determine the work done by a variable force, the answer lies in integral calculus. It's like piecing together a jigsaw puzzle. Each tiny piece, or in this case, infinitesimal quantity, contributes to the bigger picture. Integral calculus allows us to make sense of complex shapes and patterns, transforming the seemingly impossible into manageable calculations. So, integral calculus is all about accumulation and making sense of the whole from the parts. Try adding up numbers forever. Intriguing, right? That's what infinite series is about. Now, let's delve into the intriguing world of infinite series. This is where we investigate infinite sums of terms in mathematical sequences, such as power series. You might wonder, how can we add up an infinite number of terms? Doesn't it just lead to infinity? Well, not always. There are certain conditions where these series can sum up to a finite number. This fascinating concept opens up new ways of understanding the world around us, and forms a cornerstone for mathematical predictions and calculations. Imagine, for instance, that you're trying to calculate the total distance covered by a bouncing ball. Each bounce covers a fraction of the distance of the previous one. If you add up all these fractions, you're essentially dealing with an infinite series. Infinite series, thus, helps us make sense of infinite sums. It's like finding order in the chaos of infinity, a truly remarkable concept, isn't it? Ever wondered how we predict weather or model population growth? The answer lies in differential equations. Differential equations are a unique type of mathematical equation that involve derivatives. Derivatives, if you recall, are all about rates of change, which makes these equations incredibly useful for describing dynamic systems, things that change over time. So when we're talking about predicting the weather, we're looking at a host of changing variables: temperature, humidity, pressure, wind speed, and so forth. These variables are interrelated, and their rates of change can be modeled using differential equations. The same goes for modeling population growth. Birth rates, death rates, migration, these are all changing factors that can be expressed as rates of change. And once again, differential equations come to the rescue, helping us to build mathematical models that predict future trends based on current data. So, differential equations help us create mathematical models of the world around us. Now let's venture beyond the ordinary with real and complex analysis. Imagine stepping into a world where numbers aren't just simple quantities. They're multi-dimensional entities with real parts and imaginary parts, each with their own unique properties. Welcome to the realm of real and complex analysis. In real analysis, we rigorously examine real numbers and functions. It's like having a microscope that allows us to see the intricate details of numbers. We look at concepts such as limits, which allow us to understand what happens to a function or a sequence as it approaches a certain point. We delve into continuity, which gives us insight into the unbroken nature of functions. And we explore convergence, which tells us whether a sequence or a series approaches a specific value. Now let's add another layer to this world with complex analysis, where we study complex numbers and functions. Complex numbers are like numerical chameleons, changing their behavior based on the situation. They consist of a real part and an imaginary part, and are often represented on a two-dimensional plane known as the complex plane. In complex analysis, we investigate the behavior of complex functions, including their singularities, or points at which they do not behave as expected. We also delve into fascinating theorems like Cauchy's theorems, which provide profound insights into the nature of complex functions. Together, real and complex analysis form the backbone of mathematical analysis. They allow us to understand the properties of numbers and functions in a more profound way. Whether we're studying the behavior of a physical system, analyzing a mathematical model, or unraveling the secrets of the universe, these tools give us the power to see beyond the ordinary. Real and complex analysis, therefore, allow us to delve deeper into the mathematical world. Let's now explore the structure of sets with topology, and unravel the mysteries of integers with number theory. Delving into topology, we find ourselves studying the properties of space that are preserved under continuous transformations. Imagine stretching, twisting, or bending an object without tearing or gluing it. These are the transformations we talk about in topology. We're not interested in exact measurements, but rather in the broader picture. Concepts like continuity, compactness, and convergence make a grand entrance here, helping us understand the structure of sets in a more nuanced way. Now let's shift gears and venture into the fascinating world of number theory. Here we're primarily concerned with integers and their intriguing properties and relationships. Ever wondered why some numbers are prime or why certain patterns emerge in sequences of numbers? Number theory is where we seek answers to these questions. It's like a treasure hunt, where integers are the clues leading us to profound mathematical truths. One might wonder, what's the connection between these two seemingly disparate fields? The answer lies in the deep structural relationships that they uncover. Topology gives us a lens to view the world, not in rigid shapes but in flexible forms. It's about understanding the essence of structure, rather than the specifics of form. On the other hand, number theory is all about relationships. It's about finding patterns and connections among integers, the building blocks of mathematics. It's not just about individual numbers, but about the tapestry they weave together. These two fields together provide a rich framework for understanding the mathematical universe. Topology reveals the structure of mathematical spaces, while number theory uncovers the relationships among numbers. They are like two sides of the same coin, each providing a unique perspective on the landscape of mathematics. Topology and number theory, hence, provide us with a framework to understand mathematical structures and relationships. So, we've journeyed through the captivating realms of mathematical analysis. We've seen how differential calculus helps us understand change, and integral calculus allows us to accumulate quantities. We've ventured into the infinite series, adding up to infinity, and explored the world through differential equations. We've gone beyond the ordinary with real and complex analysis, examining real numbers, functions, and the behavior of complex functions. We've discovered the structures and relationships in topological spaces and number theory, and acknowledged the power of functional analysis in studying function spaces and linear operators. All these branches of mathematical analysis are not merely abstract concepts. They are tools that help us comprehend and navigate our world, from the physics that govern our universe to the engineering marvels we see around us. So when we grapple with these mathematical concepts, we are actually decoding the language of the universe. Remember, the world makes more sense when you view it through the lens of mathematical analysis.